complex models need complex problems, or vice versa, complex problems need complex solutions, so we might think. And if our complex model doesn't work, we'll just make it more complex, and so on. Albert Einstein once said, "Make everything as simple as possible, but not too simple." Today, I will talk about our research at the Max Planck Institute for Human Development about simple solutions to complex problems. The key message will be that we need to distinguish between situations of certainty and uncertainty. In Frank Knight's terminology, between situations of risk, where we know everything, and where fine-tuning pays. That means complexity pays. And on the other side, situations of uncertainty, where fine-tuning does not pay, makes the model more fragile, and leads to surprises again and again. So the key message will be, there's a distinction between risk and uncertainty. Good decisions under risk do not transfer necessarily to good decisions under uncertainty. And second, we should engage systematically in the study of tools for dealing with uncertainty. And I will focus on one of these tools, namely heuristics. A heuristic is a simple rule, and heuristics have gotten a bad name in behavioral economics. But because they've never really systematically been studied, not formalized, and not tested competitively. So what I want to do with you today is to give you 3 examples of complex problems where simple heuristics can do better than optimization models, where they can lead to safer solutions and to faster solutions. And then in the second part, I will sketch a more general underlying theory that helps us to understand when less is more. That is, when ignoring part of the information pays, when simpler models pay because they reduce estimation error and overfitting. And at the end, I hope that some of you will engage in a systematic study of tools for uncertainty, and the others at least will have a sleepless night. So let's start. The distinction between risk and uncertainty goes back at least to Frank Knight. It is being taught in almost every textbook in economics and finance and immediately forgotten. The typical models are made for a situation of risk, where a situation of risk is where we know all alternatives, all consequences, and the probability distributions, for sure. In that world, fine-tuning pays. And this is the world of the standard economics and finance models. So if you go to the if you play the roulette this evening in the casino, you can be absolutely certain what will happen, and everything that you need is probability theory. And you can calculate how much you will lose in the long run. So, but most of the problems we deal with have a certain degree of uncertainty. And between risk and uncertainty, there's a continuum, and that is why we have to think about how much calculation and how much data we should ignore. And in that world, it's no longer true that you can calculate the optimal solution. Optimization is a fiction. Second, it's no longer true that the models that give you the best answer on the risk are the best answers for uncertainty. And here, by statistical principles that I will explain in a minute, we are often better off by simplifying. And the key problem is how much to simplify, and not too much, as Einstein said it. So I'll give you 3 examples from various domains to illustrate the point, and then I go into the details. That's the program. Are you ready? Then let's start. Is there anyone who plays baseball or cricket? 2 people. Soccer? Okay. A dozen, roughly. A ball is coming in high. An experienced player knows immediately where to run to catch or stop the ball. How does he or she know? It's a complex problem. There's wind, there's spin. And the typical answer is, if it's a complex problem, we need a complex model to understand it. That's the version that I will not represent today. The other alternative is, it's a problem under high uncertainty, and we need to see whether we can find a simple solution. Let's start with the complex solution. What's that? Probably you might think that a player somehow calculates the trajectory of the ball and runs to the spot where the ball will come down. Have you ever calculated a trajectory? That's how it goes. And the problem is not computation. The problem is estimation. And that's very important to understand. We can compute today almost everything, but not estimate. For instance, alpha is the initial angle from which the ball was thrown or kicked. And that would have been estimated in a second or two. And you also may notice that I gave you a simplified version. There is no wind, no direction of wind and speed, there is no spin. So, but how else could a player solve this complex problem? A number of studies show that experienced players use a handful of simple heuristics. I'll show you the simplest one, which works if the ball is already high up in the air. And it consists of 3 building blocks. First, fix your gaze on the ball. Second, start running. And third, adjust your running speed so that the angle of gaze always remains constant. This player does exactly that. Observe how the player is running, and the angle of gaze always remains constant. What happens then? The player will be exactly at the point where the ball is coming down. We want to see it again? The important thing is that this player can ignore all the information in the formula that you just saw, and also he can ignore the information that I left out of the formula, and focus only on one variable, which is the angle of gaze. This is an example of a heuristic from a larger class of one good reason heuristic, and it shows you that it can solve the problem actually, while the trajectory computation model will fail, not because of computation, but of the estimation problem. And the heuristic is also safer and faster. If you have a dog at home and throw a frisbee, then you will observe that your dog doesn't try to calculate the trajectory. It will run in a way to keep the optical angle constant. It does exactly the same thing. In our research, we study experienced decision makers who often make decisions intuitively and work out the underlying heuristics. For instance, a ball player makes these decisions intuitively. Have you ever interviewed a soccer player? Mostly. The player doesn't know, but the player can solve the problem without knowing, and that's called intuition. And I should not denigrate intuition. So we study the intuitions of experienced experts and then work out the underlying heuristics and teach them explicitly so that others can use them to make faster, safer, and better decisions. Here is an example. You may remember the miracle of the Hudson River. A plane took off in LaGuardia Airport in New York, and after a few minutes, something unexpected happened. A flock of Canadian geese collided with the plane. The engines of modern jets are designed in a way so that they can digest birds, but not Canadian geese. They are too fat. And the impossible happened. They flew in both engines, upon which the engines shut down. It became silent in the plane. We know from the passenger reports that there was no panic, there was prayer. The 2 pilots, Sullenberger and Scales, turned around and had to make a decision about life and death. Will we make it back to the airport, or do we have to take a more risky alternative, going into a river with a jet plane? How did they make this decision? So did they calculate and estimate their trajectory? No, they didn't. They used the same heuristic, now explicitly, and in the case of a sailing plane, it goes like that. You fixate the tower of the airport through the cockpit windshield, and if the tower goes up in your windshield, you will not make it. You will hit in below. And that can be done in a few seconds and left the pilots time to go into checklists. And the checklist, going through checklists is the opposite from a heuristic. And what we usually need is a good collaboration between simple and complex tools. So this example illustrates that, first, Heuristics are not the stupid causes of all human disasters, as you can learn in behavioral economics today. Second, heuristics can enable better, safer decision-making by ignoring much of the information, and in this case, by reducing the entire estimation problem. And third, one can teach heuristics explicitly, and it's also incorrect that you read in textbooks that heuristics are unconscious. No, every heuristic can be used conscious and non-conscious. Let's move on to the systematic study of heuristics. And here it's important to follow 3 methodological tools. First is formalize the heuristic. Even if it's simple, you need to formalize it, otherwise you will never find out how good or bad it is. So it has become a tradition to use words like availability, which are never formalized, and which explain everything after the fact but cannot predict anything. That's not my vision of heuristics. And second is, after formalizing, test how good they are and test them competitively, typically against complex models. And that also should hold for those of you who are in love with complex models. Test your complex models competitively against a simple heuristic to learn how they are doing. And third, testing should not be in fitting your parameters to already given data, but in real prediction of the future. And these principles are often violated. In particular, much of success of optimization model is claimed by just fitting parameters to data. That's not what you need. That's hindsight. So consider the following problem. You own a large company. You have a customer base of 100,000 of customers, and you send information like catalogs or special targeted offers, and you don't want to send information to customers who will never buy from you, so-called inactive customers. Question is how to predict which of your customers will be active and which one will be inactive. This is a highly difficult problem. The usual answer to deal with a complex problem is a complex model. And what I show you here is a typical example of such a model in marketing, and it's called the Pareto negative binomial distribution model. It makes a number of assumptions, which I'm not going through. And again, the problem is not the computation. The problem is the estimation of its parameters from samples. And as long the world is stable and highly predictable, and you have large samples, estimation is fairly okay. But this is a problem which is highly outside on the end of uncertainty. What is the alternative? In one study, the observation was made that experienced managers rely on a simple heuristic to solve this problem. It's called the hiatus heuristic. If a customer hasn't bought for 9 months, classify as inactive, otherwise active. You can change, depending on your business, the time interval, but it's again a heuristic that pays attention to only a single variable. Now you might think the Pareto negative binomial distribution model must be better because it has all the information and more. I would advise you to do the test. And 2 professors of marketing who believed in the that complexity needs complex models did the test, and here is what they found. There were 3 companies. In the airline, the Pareto negative binomial distribution model, the brown column, made 74% correct prediction. That's impressive, unlike you test competitively. And then they found out that the simple heuristic does better. In the apparel business, the advantage of the simple heuristic was even larger. And in the CD Now business, it was the same. You just saved all the time about estimating and computation. What you see here is called a less is more effect. Let's be clear what that means. It means that if you have a certain body of data and computation, as the Pareto negative binomial distribution model uses, if you take only a subset of this data and ignore all the estimation in that case, or make it simpler in general, you may do better. Not only faster and save money, but actually make more accurate predictions. That sounds against the common spirit of big data analytics, and it is. And I'll give you in a minute the explanation why this happens. I just want to go back. So we know a number of situations where making it simple, as Einstein said, but not too simple, actually pays. So a final example that you probably know very well here. Assume you have a certain sum of money, you want to invest it. You don't want to put everything in one basket, but to diversify. How? That's the question. How much in each of N assets? Harry Markowitz from the University of Chicago got his Nobel Prize in economics for the solution. And that's the mean variance portfolio or mean variance model. I assume that every one of you knows this. And again, the problem is not the computation. The problem is the estimation of all these parameters. And they increase exponentially with the number of N. But Nobel Prize, optimization model, problem solved. So we might think. When Harry Markowitz made his own investment for the time after his retirement, he used his Nobel Prize winning optimization model. So you might believe. No, he did not. He used a simple heuristic that is known under the name 1 over N. Allocate your money equally to N assets. So this is a heuristic that ignores all data. While Markowitz optimization needs tons of data to do the parameter estimates. So how good is 1 over N compared to Markowitz optimization? In one study, 7 investment problems were studied, such as one of them, 10 American industry funds and allocate your money. With Markowitz optimization, you need many years of data. In that example, it was 10 years of stock data. With 1 over N, you need nothing. You're done. What was the result? According to standard measures such as Sharpe ratio, 1 over N made more profit than Markowitz optimization in 6 out of the 7 problems. Again, a less is more effect. And so when does this happen? The real question is, can we identify the environments where less is more or where more is better? That is the real question. We call this the question of ecological rationality. I give you first some qualitative characters. So on the left side, we have the situation of risk. On the right side, the situation of uncertainty and everything in between. So if you are in a situation with low uncertainty, that means the world is stable, and the future is like the past. And few alternatives and high amount of money, then make it complex. That's the world of complex solutions. That's the world of optimization, such as mean variance. But if you're in a world where tomorrow is not like yesterday, or at least you don't know it, when you have many alternatives, so many parameters to estimate relatively few data, make it simple. That's the world of heuristics. And there is a large continuum in between. One can put this quantitatively. One can ask the questions, assume you have 50, N equals 50, say 50 assets, and how many years of stock data would you need so that the mean variance model has a good chance to get better than 1 over N? Remember, in the study I just reported, there were 10 years of stock data. So how much more do you think? The answer to this question can only be given by computer simulation, but it helps to think. So what do you think? How many years of stock data would one need so that the Markowitz optimization finally gets its parameter estimations under control and gets that we can expect it being better than 1 over N? 10 years is too little? 12? 15 years? 20? The best estimate is 500 years. That means in the year 2500, people can stop trusting simple heuristics and do the calculations, provided the same stocks are still around in the stock market in the first place. Do our banks understand this important connection between simplicity and an uncertain world and complexity and a certain world? I'll show you a letter I got from my internet bank, and the letter was sent to all customers, and it's in German, but I'll translate. It says, with Nobel Prize winning strategy to success in investment. And then the letter read, do you know Harry Markowitz? No, because Germans have no idea about finance. But he should, and then they explained that he won the Nobel Prize in economics. The bank is now doing Markowitz optimization, a little bit late, but anyhow. And then there was a warning about your too simple strategies and your intuitions. What this bank has not understood is that they sent the letter 500 years too early. So let me now come to the second part and give you an idea about a more general understanding of when simple heuristics pay and when complexity pays. So far, I just gave you 3 examples. Why do people use heuristic? The standard answer to this question in behavioral economics is because heuristics are simple and they need less effort, less information, but you have to pay a price in terms of accuracy. Your predictions won't be as well. This is the view that you can still read in Kahneman's book, Thinking Fast and Slow, and it is not correct. It is only correct in the world of risk. In the world of risk, heuristics are always second class, but not necessarily in the world of uncertainty. Formally, this view means that your total error of your prediction instrument has 2 components: bias, so a systematic component, and noise, some kind of unreducible error. The moment you make actual predictions under uncertainty, the situation is different. It is characterized by the bias-variance trade-off, well known in machine learning, not so well known in economics. And here there's another component that's called variance. Variance is basically the overly sensitivity of your algorithm to the specific properties of a sample. Or in other words, if you take many samples from a population and estimate your parameters, you get a variability across the parameters. I'll explain this with a simple picture. On the left side, there's a dartboard. On the right side, there's another one. The player on the left side has a systematic bias. He is throwing too low and too much to the right. The bias is defined by the difference between the bullseye and the mean dart. At the same time, the player has a low variance. On the right side, there is a player who throws all over the board. But this player has no bias. On average, the darts are exactly in the bullseye, but only on average. The variability is high. So that illustrates that a model with a large number of parameters and a high estimation problem, even if it's unbiased, will lead to something on the right side. Predictions all over the place, depending on the specific sample. And you can do better with a simple model that reduces variance. For instance, 1 over n has no free parameter, so it will always give the same dart throw. So there will be no error due to variance, only error due to bias. Markowitz may have a smaller bias, but it creates, depending on the sample size and the number of parameters to estimate, much more variance. I think this is a good way to understand that the question is not to just look at the bias and make it as low as possible, but there is a trade-off between bias and too much variance. A simple heuristic with no single free parameter, as you just saw in the hiatus heuristic, if you keep the 9 months constant, or in 1 over n, will have 0 variance, only error due to bias. And that's how one can understand that one can do better by designing models that reduce variance, not only bias. Here's an example. Here you see the temperature in London. These are 365 points, average temperature. And assume that could be financial indices. It doesn't matter here. You want to know what's the underlying, you want to model this, what's the underlying process, and assume you think in terms of polynomials. Here we have a polynomial of degree 12 and one of the degree 3. So the simpler one is the green one, the degree 3. Question, which of the 2 polynomials fit the data better? No? Shouldn't be so difficult. Yeah, right, the red one. Yeah? It has more degrees of freedom. And if you want to have a perfect fit, use a polynomial of degree 364. But fit is not the goal of science, nor of an investor. You want to predict. So what we do now is we take a sample of 30 out of this entire population and fit these polynomials on that. Or we just take the fitted polynomials on the year 2000 and predict next year's. And what you see here is that the error on the y-axis decreases the more complex the polynomial is. And as we know now, if we just would go on, at 364 degree, we will have 0. The question is now, if we now predict, what shape will the curve have? To make it simple, let me ask two questions. Will the prediction curve, so we take every one of these polynomials and just so, this 12-degree polynomial fits better than the 3 polynomial. Huh? That's what you also see, has less error. So we take every of these and predict. Will the prediction curve be above or below the red curve? What do you think? Above, yeah. It's more difficult prediction. It's more difficult, and if you're socially intelligent, you could have seen I left more space above, so it must be there. But what shape does it have? Is it also monotonically going down, so meaning that the more complex model you have, the better you will predict? Or has it a different shape? What's the shape? Give me a sign. It's going up. Yeah, you got half the truth. It's U-shaped. So what do you see now? Think about the 3-degree polynomial. That wasn't as good in fit as the 12-degree polynomial. In prediction, it's much better. It has less error. And you may also see the interesting fact that a 1-degree polynomial, which is just a line, which is not a good model of temperature in London, has a total error that is smaller than the great-fitting 12-degree polynomial. And that's mostly due to error. So what does this show? It illustrates that by making overly complex models that try to take care of every potential causal variable or whatever it is, we risk creating models that systematically mispredict the future. And the alternative is make it simple, but not too simple. Not 1 degree, but here like 3. So let me come to the end. Yeah. I showed you today 3 versions to make things simpler. One is to use equal weights and do not even try to estimate the weights in order to reduce estimation error. Second, one-reason heuristics, such as the hiatus, and lexicographic heuristics I didn't show you, but you can read about that. So here's the key message. Situations of risk are not the same as situations of uncertainty, despite almost all economic theories just pretend to deal with risk. Second, heuristics are not a tool that explains why we are dumb, but they are useful tools in a world where optimization is a fiction. Nassim Taleb calls this the turkey illusion. And finally, robustness is the goal under uncertainty, not optimization. And complex problems do not always need complex solutions. We should have the courage to look out for simple solutions rather than to something that looks impressive mathematically but doesn't do well. Less can be more. Thank you for your attention.
I'm honored to come back. Actually, was someone here, did someone attend RISC-Mind? The first one, I think, was 1999. I gave a lecture in 1999 that's sort of similar to Gerd's lecture against Markowitz. And I said, unsafe at any speed, it was called. And I'm going to use some of the graphs here. And effectively, all I'm doing is continuing Gerd's presentation because he sort of happened to be the only academic I agree with. Let me start. You know, Montaigne has a saying that he prefers the company of peasants to he prefers the company of the uninformed to that of the misinformed. Okay, so we have this whole class. My war has been historically as a trader, and in '99 when I gave the first lecture, I was still a trader. So I was dressed in jeans, by the way. Now that I'm not a trader, I'm not allowed to wear jeans. They said. The idea is to debunk pseudo-experts and view the world the way we view it ourselves. Visibly, if you want a pseudo-expert, you have one here. So we've been living plagued with that expert problem. People who think they can run your life, people who think you can do things. And effectively, that was sent to me this morning from the China Morning Post. It looks like we're in a situation where people are finally realizing that there is a generalized expert problem. That effectively many of the people we call experts, on paper, look very impressive, but they can't find a coconut on Coconut Island. And you can fool voters, you know. You could fool voters in 1960, you could fool voters in 1980, you could sort of fool voters in 2000. 2017, it's much harder because there's something called Twitter. And also, we're going to see why these experts aren't that expert. Let me take a simple case. You know, I like to give mathematics in the morning to just wake people up and then move back to more entertaining stuff. So we're going to talk about scientific papers. And this talk is pretty much about how your grandmother knows more about things that are scientific, and is vastly more scientific in many instances than scientific papers. Because people have the feeling that if the paper is published in Nature or in some journal, that it is true, okay? And they base their studies on something called p-values, okay? So if you believe in p-value, right after this, I have two bridges, one in Lebanon and one in Brooklyn, you know, that we can negotiate later. If you believe in p-values, but people tend to believe in p-values. And the thing blew up in Kurzweil, psychology with his enemies, when someone attempted to replicate 100 papers published in, say, called the best journals in his field, psychology, in 2008. Of the 100 papers, how many replicated, in your opinion? 95? It was only, how many do you think replicated? Sorry? 39. 39 replicated, and of the 39 that replicated, few had the same effect as originally announced, okay? So in other words, it was true. And the reason is that people don't realize what p-value means. Say I take a p-value is a stochastic variable. It's mathematical. This is a simple mathematical application of, you know, continuation. Is that you think you have a number, like value at risk. It is not given by God for future experiments. It is something that results from a simple sample. So if you take the ensemble, if you repeat the same experiment many times, effectively, if your true p-value is something like 0.12, 12%, 53% of the time, you're going to have values below 5%, and 25% of the time, you're going to have value below 1%. Okay? That's straight p-value. But there's something actually worse. Is that these experts, what they do is, not only they already have a flawed metric to tell us if something is statistically significant, if the result works, but they do something vastly worse. They do a lot of experiments, okay, and take the best. That's why they get funding. They're paid to publish papers. They're not paid by reality. They're paid by some institute that gets funds from some institute, okay? So you publish M-Trial. It's exactly like Fidelity in the old days that have 100 funds, and then they show you the performance of the top 5. And somehow, the funds would go into cyberspace, okay, would disappear. Okay, the non-performing ones. Survivorship bias. The same applies here. So if your effective p-value is 0.12, okay, you can bring it down to 1% simply by doing 12 experiments and picking the best of these 12 experiments. So this allows us to debunk already some expert problem by saying your grandmother has conveyed heuristics through generations. So if she's better than 50% reliable, she's better than the expert, because the expert is not reliable. We're talking about a war against these experts. They've been wrong on Stalinism, Salafism, dynamic stochastic equilibrium modeling. I'm sure many of you are familiar with that nonsense. Okay, portfolio theory, Markowitz that is, the Iraq, WMD, housing projects, selfish gene, country risk, recessions, predictions, all that. Lobotomies, by the way, okay. So, and you want us to believe him next. Now comes a deeper problem. And that's the topic of my next book, the 5th volume of what I call the Incerto. The Black Swan is the one people know me for. Hopefully, they will forget about the Black Swan, remember Antifragile and the Incerto as an overall, project. And that was what I showed in 1999 in that problem with the experts. If you not paid by reality, but paid by perception, how good the job you're going to do. And say I have a portfolio to manage. What do? I show small gains, okay, and once in a while, a huge loss, okay? In other words, I'm going to be short some out-of-the-money option for a very simple reason. When I make money, I get something called a bonus. Some of you, it's this time of the year, so some of you are familiar with conversation about a bonus, okay? So you get a bonus when you make money, and when you blow up, what do you get? No bonus, all right? Do you have something called a negative bonus? No. But if you trade your own money, you have a negative bonus, you see? So that asymmetry, okay, created a whole industry of experts who were never penalized for being wrong. Take the New York Times. The New York Times really got us into Iraq with the WMD, thing. Did they have to write a check for the losses we incurred for the people who starved in Iraq? No. Even the financial, no. You take a journalist like Thomas Friedman, he just wrote another idiotic book. He wanted us to go into Iraq. He was wrong. Did he pay price? No. When he's right, he collects a little bit of bonus, and he reminds you of it. So really, this is what the problem is, lack of skin in the game. And effectively, what skin in the game does to you is it is the only disciplinarian. And it's remarkable that someone like Professor Gigerenzer, coming from academia, realizes that people who have skin in the game for themselves, I mean, it's rare, maybe 10% of academics understand the concept of skin in the game, and only 1% go all the way to look at its impact. Because those who have skin in the game don't look for complexity. What do they look for? Simplicity. Because in the real world, you're not judged by some supervisor who's going to write a report. You're judged by your accountant, okay? So there is something, that old parable of after huge labor, the mountain gave birth to a mouse. So there are two worlds. A world in which you want the mountain, something very sophisticated, to give birth to something as simple as a mouse. And then the other one, you want the mouse to give birth to a mountain. In academia, it's pretty much about mouse give birth to a mountain. So we're going to compare two projects in finance, Markowitz versus Thorpe. I had, after drinks with Gerd last night, visibly he made the case for Markowitz, okay? That Markowitz doesn't work in practice, but works in academia because it is very complicated. As you saw his equations, it works. He is like a basketball player. So we have Thorpe. I don't know how many of you have heard of Ed Thorpe. Ed Thorpe is the fellow who wrote first the book called Beat the Dealer in gambling. He was an MIT faculty and mathematician, and he met the information theory people. And they started going to casinos and gamble, okay? And they made tons of money using very simple heuristics. And his heuristic was, in blackjack, instead of counting cards, which, the combinatorics are hard enough for a computer, you just take the deck and you look, a strong card, you +1, and a bad card -1, and when the deck hits something like +5, you start betting. That's it. So because you have the edge over the casino in some circumstances, and a very simple heuristic that could be applied by anyone who knows to count till 5. You know how to count till 5? Very good, you can get rich. So that was his technique. And then later on, he came to finance. And effectively, he popularized and formalized something called the Kelly criterion. Does anyone here use the Kelly criterion? But anyone who gambles his own money uses a version of the Kelly criterion. From Warren Buffett to all these people. What's the Kelly criterion? Here, you have to know the future and the joint distribution of return ad infinity, okay? And with precision, because a little bit of failure of getting, the precision blows up your optimal allocation. In this world, all you need to know is two things: expected return and how much you're willing to lose. And you go one step at a time. You see, every morning you have coffee and then change your portfolio. And that's the Kelly criterion. This is information theory, computer science. As he said, again, bias variance is well known in machine learning, and machine learning is within that school of thought. And here is people who try to sell either themselves, write for something called the Journal of Finance, which has never produced any article of note for reality, but helps in tenure. This is an academic world, or the pseudo-expert world, the one that's exploding as we speak across the world. From from India to Brexit to the US. Brexit was mostly a vote against these people, these pseudo-experts, or these so-called experts. So another case of so-called experts, I went to work for the IMF, where they do stress testing, and I presented about 2 years ago that paper. That technique to test tail risk was a very simple heuristic. And they wrote a paper, and they think they're going to get it in their procedure in 2028, okay, to tell you how. It was too simple, so they couldn't believe that it works. It was very simple. All you do is do stress tests at 20%, 22%, 24%, see if you have acceleration. If you have acceleration, you're in trouble. If you don't have acceleration of losses, you're not in trouble. Very simple procedure, but it's too simple for them. So they're delaying the implementation, although it's one of their, it was working paper that published in one of their books, and then later on, maybe make it to procedures. Another example, I've been in a war against GMO, genetic modification, which is proposed on grounds of, we're going to feed the planet. Okay, again, same pseudo-experts, they want a complicated solution. We discovered the following. If someone shows up in a doctor's office, the first rule we know since the beginning of medicine, or since the Hippocratic Oath, is first do no harm. So the first thing you do is try to tell him to have a good night's sleep if he has a headache, all right? Where the expert would propose immediate brain surgery because it looks more scientific. So likewise, or you give him an aspirin if you have to do something. You don't, do brain surgery if an aspirin could do, all right? So that's a simple rule in medicine that took a long time to implement in Western medicine because you had that fear of not being scientific. And now we understand that science doesn't look scientific. Science is heuristic. And science is, again, in simplicity, because the more complex something is, the more side effects it will have. So the same thing with, they want to do GM rice, something extremely complicated. Okay, so instead of give people rice and vitamins, you want to combine them in something that has not worked, but is very profitable, would be very profitable for Monsanto and other firms. So instead of doing this, okay, to solve world hunger, just solve a simple transportation problem. The world hunger is a very simple distribution, issue. It is not something to do with production, because most of the difficulties come from distribution of food. So, but it's too simple. And we have shown actually that a banana is not the same risk as all these complicated genetically modified organisms, because when you do things naturally at low speed, like, or the apple, we do effectively modify crops progressively. But the way we modify them is by staying within what we call the viability island. And if you jump a viability island, all bets are off. We have no idea scientifically what it can take us to, you see. So we were taking monstrous amount of risk, actually for no return, because we're shown that basically these are more expensive. So it's riskless returns. But it's very good for the experts because it looks more scientific. So the area where there is a big expert problem, as I'm saying, your grandmother would not like GMOs, and she's right. Another case of don't think that because the expert said they're good, that they're good. Actually, we noticed no tail risk study. And mathematically, if you know mathematics very well, then you're probably at par with the grandmother, you see, to know that mathematically the risk metrics are not sound. Like mathematically, Markowitz, anybody who knows mathematics would realize that Markowitz cannot work in practice under fat tails. So nonlinearity, nature has a mechanism by which it works, which brings us to the general problem of complexity, okay? When you are trained in linear methods, you think that you can solve problems with the tools you have. But when you understand complexity theory, you realize, hey, it's not that simple. Or it could be simple, all right? But you have to approach things differently, using different methods. So what the characteristics of complexity are first opacity. You don't see what's going on in the system. The second one is interaction between components. They interact. And that's quite central. And the third one is fat tails. Fat tails means, of course, things like, I don't have to explain fat tails because I guess this is, I've done nothing else all my life except study fat tails. But we summarize the fact that a rare event dominates the properties. But now when we look at interaction, you realize you cannot generalize. You cannot generalize to a school of fish from the observation of a single fish. And this has pretty much sunk behavioral economics. And let me explain how. Assuming the biases that we humans have, according to these pseudo-specialists or specialists, are right, assuming they exist, they still cannot generalize to market behavior. Because the market is not driven by the average, it is driven by people plus interaction. So you cannot really see how things aggregate from studying individual behavior. So we can all be stupid and the market can be smart, okay? Or we can be stupid on average and the market can be very smart. So you can't really claim market had these biases based on observed biases for individuals. And that's mathematically, okay? Can be done mathematically. Now we're going to hit something that I think is quite consequential, that I've been thinking about it almost all my life, but it was formalized by this fellow here. I don't know if you see this fellow. He's a happy man. He's Murray Gell-Mann. I don't know if you know who Murray Gell-Mann is. He's an American physicist, Nobel Prize winner. He's probably the most decorated scientist alive. He discovered the quarks. He is a very, 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 very smart fellow. And he's one of the founders of the complexity works at the Santa Fe Institute. And with a fellow, they discovered the following. So let's talk about something quite central in finance and portfolio theory. All of us have this illusion of thinking that if you look at average returns in the market, and assuming that you have the right metrics, that they will apply to you if you trade. Effectively, wrong, wrong, wrong. Let's talk about path dependence and why it is central. I don't know if you can try the experiment, but let's do the following experiment. First, you iron your shirt, and then you wash it. Okay? Second, case 2, you wash your shirt, and then you iron it. Okay? You get different results, no? Aha, so the sequence matters. Okay, so we're going to see, let's talk about sequence. This slide, actually, I had been working on this, I've been conveying this, I've been giving metaphors about this, but didn't hit me till I saw it treated by Murray Gell-Mann, and he and his co-author effectively have disturbed everything we know about probabilities and Bernoulli by showing the following. Let's say that we have 100 people, okay, 100 people go to the casino, all right? 100 people. Number 29 goes bust. You see, when he's bust, we put him head down, okay? He's ruined. What happens to number 30 if number 29 goes bust? Will he go bust? No. And then you can take the average return from all of them, and let's say the casino gives you the edge. You can take the average return of all of them, no? Divide, and so on, reduced by the person who went bust. So this is what we do, it's called state space methods. Lattice state space methods. Everything in finance is based on these methods, which is basically to take the expected return, all right, from this. Unfortunately, if you take any speculator and make him go to the casino 100 times, and on number 29, that is day 29, not speculated number 29, it's day number 29, the speculator is bust, head down. What happens to day number 30? There is no day number 30. Okay, so this is very simple here. So this is called the ensemble average, and this is called the time average. They're not the same. Any speculator subjected to ruin will eventually be ruined. It's only a matter of time. It may take 10 years, 5 years, or a billion years, but it will be ruined, okay? So you gotta look at stopping time of ruin. This we know as option traders, that all these analysis of option selling don't count, because eventually if you are ruined, you're gonna be ruined, okay? So this is what we call, so there's something, for these two to match, you need something called ergodicity. And this is only satisfied by what we saw with my friend, you see, sorry, Markowitz, the ugly guy, versus the better, fit guy at Thorpe. Kelly criterion is ergodic. It's a strategy that allows you to capture the effective alpha of the market. So your alpha matches the market only on the condition of absence of ruin. So this is quite annoying. Actually, classical risk theory got it, okay? And it's quite annoying because it disturbs a lot of things we do about valuation, okay? Valuation, by taking market return, doesn't apply to valuation to you individual if you have what we call uncle point. You take the alpha of the market. If at some point the value drops to some level and you panic because, hey, you know what? You don't want to take additional risk. And age 65, people retire. In Europe, no. In America, it's age 87 and a half where people retire, but okay. But you're retired, now you depend on retirement income, and you want to keep buying the Cuban cigars, and this is the level we can no longer buy Cuban cigars, so you cut your position. Guess what? You cannot, your alpha will no longer match the market, you see? Particularly if there are panic dips and stuff like that. So basically, this is, and what Murray Gell-Mann, who's a great mathematician, great physicist, great scientist, great mathematician, basically he said, except for the information guys, all you guys, Markowitz, all these things, and everything that has been done pretty much in lattice state space method is bogus. I'm not, he said it. He said it doesn't work. And a lot of people have made that mistake. He named them. Decision science, decision theory. So now let's talk about psychology and psychological experiments. Basically, what people don't get is that if your grandmother is paranoid about small risk, you cannot tell her, No, it's only a small risk for the following reason. You can never analyze risk-taking as one-shot experiment the way psychologists have done it. They tell you, well, do you want this bet, this bet? Oh, he overestimates small probabilities. You can't. For this following reason, you're always exposed to negative probabilities, okay? And if you take risks, say, do this on a weekend, okay? While at the same time smoking cigarettes, and at the same time having knife fights with people in the mafia, once a while, visibly, you have to add up those risks. And what happens to you when you add up all these small little risks? We go bust. So the way to analyze risk-taking is not by taking one static thing, but over time, assuming how many tail risks you're going to take over your lifetime, your remaining balance of lifetime, not a single thing. And before Barry Gell-Mann, nobody formalized it. Every trader knows it. Every single person who partook of the no-ruin thing in insurance knows it. But it's not in the finance literature. That's the mother of all expert problems. And if you take behavioral finance and biases, assume the agent will never again take the same risk. But we take these risks. So if you do it that way and assume risk is cumulative, then basically there's absolutely nothing irrational about worrying about GMOs. As people want to pathologize us for worrying about GMOs. This fellow works for Obama, and I'm so glad. He can still work for Obama, but with no impact. He actually, incidentally, is an enemy of GERD, no? I mean, let's say academically he's an enemy of GERD. He's a personal enemy of mine because as you can see the difference, GERD is much more polite than I am. All right? And this guy says, oh, precaution is irrational because it's unscientific. But when you think about it, you do real science, you realize that effectively, we have to be more and more paranoid as we go up this ladder. So you have to be paranoid about yourself, but that's okay. Because if I die, it's not the end of the world, okay? I'll only lose my remaining life expectancy. But if family, friends, and pets, it's worse. My gene pool is worse. The tribe is worse. Self-defined, extended tribe, humanity, but ecosystem, aha. So you're losing a lot. So the more you go up, the more you have to be paranoid. So when we are worried about things that impact the ecosystem, it's absolutely not subjected to rational decision, what we call rational decision making. You should be a no-no, and that's where your grandmother intuitions are right. So if we reframe things using this background, and I hope hopefully I'll be invited again by GERD to go to a center and then try to do work along these lines, and we can see exactly where all these analyses of decision making, you see, are wrong, because tail probabilities matter overall, not just locally, all your life, if you see. And the only way to analyze things is by looking at how much it reduces your life expectancy. And if you think life expectancy is my life expectancy is an extra 30 years, 40 years, then I can take some risks. But I don't want to reduce the life expectancy of my gene pool. And I definitely do not want to reduce the life expectancy of the ecosystem. And every time you take a risk in the system, they add up. So it allows you to be aggressive in some areas and not in other areas. So I'm going to stop here because there are a lot of things to discuss. And I'm taking a bonus of about 30 seconds, GERD, for the conversation. So I'll continue that. So I can cut earlier, about 30 seconds earlier. It's never happened, I think, to me before, to continue. But thank you for listening to me. And hopefully you will be more skeptical of the experts leading this room than you've been coming in. Thank you.
This is a short discussion section, and you are invited to just pose questions, and maybe I'll start with a question I got. When I mentioned the dog and the frisbee, and one of the colleagues here pointed out that was the title of Andy Haldane's talk, the Jackson Hole talks in 2012. This is correct, and in fact, it was Mervyn King, then the governor of the Bank in England, who put Andy and myself together early in 2012. I explained him, and the first example I gave to him was the gaze heuristic that dogs use, and I explained him the mathematics below that, and Andy Haldane reacted differently than most people who say, oh, that's interesting, yes, wonderful, let me go on with my business. He said, oh, Geert, now I understand it. He did his own research on that. And when we met the second time, he said, this is my Jackson Hole talk I wanted to give. Here's the waste paper basket, that's it. And I will now give a talk on these ideas that we have started to work together. So how to make the financial system safer by making it simpler. And the analogy that he uses in this Jackson Hole talk, titled The Dog and the Frisbee, is the dog, how a dog solves a complex problem. And under high uncertainty. And that could be something that the financial, at least the practitioners, if not financial theory, could take seriously and investigate, rather than ignoring it and carrying on with the optimization models that Nassib is always willing to bash them down.
I mean, they bash themselves. One comment I want to make a connection to skin in the game that I didn't quite make tight during the conversation, during the lecture, is that why do I advocate skin in the game? It's not a disincentive, okay? It is an evolutionary thing. It's for the following reason. If you drive on a highway, any nut can kill 30 people by just, going wild. But why doesn't it happen? Well, it doesn't happen because these people are dead. You see, they're dead, so they no longer, because they have skin in the game, they tend to exit the gene pool when they make a mistake. Yeah. You see, so this is where, so we have an evolutionary thing for things to filter. Things that survive are things that have robust rules. Robust, and not necessarily the simplest, but the most robust in the way that they can survive different environments, and they don't lead to ruin. So this is the connection between skin. So this is why skin in the game, for me, is monstrously necessary. For example, you take hedge funds, and by now, about 60% of the assets of the big boss at the hedge fund, who's effectively the risk managers, are in the fund. That's skin in the game. Yeah. And it doesn't probably make them much wiser. It make them a little wiser. They can't hide risk. But it eliminates, it makes them bankrupt, go bankrupt.
So, Nassim, then, to take the Deutsche Bank. So how do we change the system so that the managers have skin in the game?
You don't want that. The system has changed automatically because all the risk-taking has moved away from banks, moved to hedge funds. It's like people tell me, how do I organize society to have skin in the game? Well, get rid of Obama, all right? Less centralization, more decentralization, the German way, where people who make decisions live in a community, like in Switzerland. So in other words, it's much easier to have a structure that is that accommodates skin in the game than try to force skin in the game in existing structures such as Deutsche Bank.
So are you saying that the solution could be, or one of the solutions, only have hedge funds, and all the banks just do traditional banking?
Well, that's exactly what's happening.
That's
exactly what happened. The risk-taking has migrated progressively into hedge funds for several reasons. Yeah. And hedge funds tend to have skin in the game. And this is why you have and the ecology of hedge funds, we have about, I counted 1 year where we had 2,800 hedge funds closing without one of them making it past the 10th page of a newspaper. Okay, so you realize, okay, so that you have, just like restaurant business, the restaurant business has an excellent ecology of people coming in and people leaving. And that skin in the game effectively acts as a filter.
So let's give the audience a chance to ask questions to both talks. There were some common ideas. So the idea that complexity should not be fought with complexity always. Yes, please. The microphone is coming.
Thank you. Yeah, at the moment there is a big push towards machine learning, especially in risk models. You only have to look at program of this conference and all sorts of student projects that I supervise all the time. And of course that yet is another jump in complexity and involved solution to a problem of, let's say, credit scoring and so on. So this development is very, very strong, and it goes completely against of what you are advocating. Yeah. And I'm with you on this, but I want to know what do you think about it, and what is the response you would give to people trying to push those very complex nonlinear machine learning methods on this, for example, credit risk problems or market risk problems or any other risk-related issues?
So. The answer is that if the problem, like predicting credibility of debtors, if you're in a situation where you are in a stable world, where things are like tomorrow, like yesterday, where you can actually have enough information to estimate your parameters, then there is a chance that the complex models would outdo simple rules. But I suspect that is exactly not the case in this problem. And I would like to see empirical studies about creditworthiness. So, for instance, we know that experienced bankers often just look at two things, if you apply for a loan in the simplest case, versus filling out all these pages of information and then running a logistic regression. So one needs to have an empirical approach for that rather than believing in complexity. And also, there is something else. In my observation, many reasons for using complex models that most people don't even understand, but they're impressive because they are formulaic, is one reason is defensive decision making. Defensive decision making means you as a manager protect yourself against being criticized or being sued. And this is your first priority. So not to actually do the best for the company, but you do something second best that protects yourself. And often relying on big data and analytics that many managers do not really understand, but they buy it in order to protect themselves. If something goes wrong, you might be accused, why didn't you do this? So, defensive decision making is a big problem. And in my analysis of large corporations, about a third to half of all decisions are made defensively. That means that the managers do not recommend the best thing for their company, but something second best to protect themselves. A huge waste of money, time, and intelligence.
Yeah, that's the skin in the game problem, exactly. Because let's take a very simple thing outside finance. If I have a doctor, I go to a doctor, and what's he going to do? You see that graph, hidden risks, delayed, and benefits. We know that Lipitor, if you don't have hypercholesteremia, or all the blood pressure thing, if you're slightly hypertensive, that these harm you more than they help you. But the point is, he's going to prescribe these things to you, because if you have a heart attack, you can sue the doctor. But if you have delayed iatrogenics, means side effects later, okay, it is so he doesn't pay for it. And so what happened is that they follow not the the optimal situation, but the one that optimizes their legal liability. Okay, and so this is the situation is effectively remedied by skin in the game.
Yeah,
and I think Gerd had a comment, is never ask a doctor what you should be doing, ask him what he would do if you were you. You already changed one layer of mental skin in the game by, I would do this.
Or if you don't ask a doctor what he recommends to you, but what he would do if it would be his own son, his own brother, his own wife. And just to add a figure to what Nassim is saying, the problem about skin in game, here defensive decision making or defensive medicine, depends on the environment. It's particular defensive prone if you live in the US. And in one study, over 800 American doctors were asked whether they practice defensive decision making, typically giving you too much antibiotics, too many unnecessary cancer screening methods, or imaging techniques, which also bring in money. And what proportion of American doctors said, yes, I'm doing defensive medicine? So in the study, 93%. And it's probably an underestimate because not everyone admits it to the other one or even to him or herself. So here's a huge psychological problem that is also relevant in finance because many people who are decision makers defend themselves and are rather willing to sink their own company.
It drew to my attention in your presentation about the certainty, uncertainty, and you said there is a somehow degree of low uncertainty. In my understanding that the risk, we defined it as the probability of occurrence. That's the level of uncertainty should be the ending line of the certainty. That when you have low uncertainty, it means that you are more certain. So there should not be somehow, the uncertainty is the ultimate end. If it is we are living in a world of certainty, then there will be no risk. The risk is that this is the level of the certainty we know. And the simplicity you have said out of the experience, don't you think that the experience is the compilation of the complications and the analysis and all the formulas that we have learned and anybody would learn by intuitive or by education, that to make his last decision simpler or even heuristics. So this is what I'm trying to say. Do you measure the level of uncertainty or you level the measure of certainty?
Okay.
And the risk.
So uncertainty has many more dimensions than certainty. You may not know what the alternatives are. So if you want to marry, there's no way to know what the alternatives are. You may not know what the consequences are, even if you know all alternatives. There's surprises out there. And even if you know, if your world is so small that you know all consequences that can happen and all alternatives, you may not know the probability distributions. You may get in problems that Nassim has been talking about, that there may be fat tails, but you cannot really estimate them. So under these conditions, by definition, you cannot optimize. And that is so self-evident as almost everyone forgets it about immediately. And one way to deal with these situations is to use, to a certain degree, heuristics. And And I emphasize, one needs to study them seriously, taking heuristics seriously and also taking uncertainty seriously. That has not been happening. For instance, behavioral economics criticized neoclassical economics about Homo economicus, wanted to make it more psychologically real, which was a good intention, but they didn't dare. And it ended up, for instance, in the book by Thaler and Sunstein, as Homo economicus is the ideal for us, omniscience, and we are Homo Simpsons. And there's no idea of critique on the model. Any deviation between the model and what you do, the blame is on you, never on the model. And we need a new behavioral economics that dares.
I have one comment on this, is that often when you hear people say that we humans are irrational, it's a person not knowing what the hell they're talking about. Okay? So this is where we go back to, if the expert, that Sunstein, I had a little thing going where they don't know enough probability to be talking about probability. That's one first comment. The other one, I'd like to comment on something I picked up to connect things to tighten things. You remember I made a comment that probability in time is not the same as probability in space, okay? And that's critical. It reminds me of a comment I heard you make 15 years ago in Munich. But we had all beer, so the comment. The first time I met Gerd Gigerenzer, he was saying that if you ask a Frenchman what does the probability of rain, 30% probability of rain, he would tell you 30% of experts think that it's going to rain. If you ask a German, he would tell you that 30 days out of the year it's going to rain. And if you ask an Englishman, he would tell you it's going to rain 30% of the time during any given day, right? So, and we see all of these can be called probability. Yes. So the word probability itself is not rigorous enough to describe many phenomena, that you have to attach what you mean by probability. And effectively in finance, it's not my idea, it's to go back to that giant, Murray Gell-Mann. It's so much easier when I present ideas I agree with and dress them up in a giant who knows definitely more math than anybody in finance and knows more about physics. And go back to physical probability, because he's a big quantum mechanic guy. What Gell-Mann said, someone talking about probability in time is talking about a completely different animal that only rarely coincides to probability in space.
Yeah. We have another question?
I'm Johannes Voigt, German Savings Banks Association. When professionals, let me not call them experts for the moment, for example, make statements on rare events, can we safely assume that there are some heuristics underlying so that it's worth following your program, like formalize it, uncover it, train the experts afterwards? Or is there something which you might call just statements from the gut, which maybe are less valid than those based on heuristics?
I mean,
and how would you differentiate?
So if there are rare events that are so rare that you really can have good statistics, then you should say that. And this is part of the world of uncertainty. I think it's an illusion if you use probability models on that thing. And that's what, Nassim, I think what you call the turkey illusion.
Turkey problem, yeah.
So meaning that in a state of
yeah.
uncertainty, you still use your probability, which is a theory of certainty probability. It just works if you know the probability distribution, period. And so that maybe I think it's much more caution and modesty necessary. And there can be heuristics that you might use, you might research for these situations rather than probability models that give you a number and suggest an illusion of certainty.
It's the same. There's a classical thing I've noticed in my experience, and it's pretty much you see it. And we did some kind of not testing, but counting incident. If you have a PhD in finance, you stop understanding something that a peasant would understand, which is the difference between evidence of absence and absence of evidence. So the minute someone has a PhD in finance, they cease to understand it. Okay, some people but if you have a PhD in math, maybe not. You see, so there's something about this half-known knowledge. They believe, and they start talking about evidence-based. All right, so there's evidence of no harm or no evidence of harm. So mixing them, the two are very, very divergent. So that's the turkey problem. So effectively, I've noticed. Let me give you a very simple example. In 1999, we looked at every single fund manager who blew up in 1998. And we had a list of them. And then we had professors of finance who went to or economics who went to the hedge fund sector. And how many of them blew up in 98? We had 39 names. 38 out of the 39 blew up. Okay? 38 out of 39 professors of finance blew up. Blew up means, experience an LTCM-like drawdown, except for one. And so it tells you that it's not, there's some exception. And then the other thing also we noticed is that when we took the ones who didn't blow up, okay, all the ones who didn't blow up, they were either mathematicians or just uneducated, fellows. So I won't disclose the names now, except, but we didn't publish it as a study, so we'll have to show the names, but you can do it yourself. Count how many, the LTCM-like, firm-like were there, and you can figure it out. There's 600 units that blew up, and you can go from there. So it tells you something about this Turkey problem, generalized Turkey problem that exacerbates with half knowledge.
Yeah. There are two more questions over there.
Wolfgang Huber from Erste Group. I would be curious about your comments on the regulatory evolution of internal models. So there are lots of discussions now going on. Is this more a trend now towards heuristics? What Basel is trying to do is going back to standard, or what the SSM is actually trying to do with a lot of publications and kind of micro-steering internal models and getting very much into the details. So how would you comment on this evolution?
So I think Andy Haldane has done a great job with his Jackson Hole talk to get this issue into this. As I see this, so the continuing increase in complexity. So Basel I was about 30 pages, Basel II over 300, Basel III over 600. What's coming next, we do not know. The Basel III people at least use now the term simplicity in their papers. To which degree that really translates is another issue. Yeah? One should realize that take the value at risk computations that come from a world of risk, not a world of uncertainty. A large bank has to estimate thousands of risk parameters, a covariance matrix in the order of 1 million. This is mostly guesswork and add the internal models. And the parameter estimates, they border on astrology. And that has not prevented, not even foreseen any crisis. But it's still done in the absence of an alternative, but the alternatives exist. And I didn't have the time. I worked with the Bank of England on designing very simple rules that could get in more safety in the system. And I think there is an alternative. And in part, it is not gone, or there's still resistance because of this illusion that you need complex models to deal with complex situation. It's not true. You need sufficiently simple models to have a robust solution. And also the regulators can see more clearly whether the banks game it or try to game it than with millions of estimates.
I want to comment that people don't think that he's saying, or that, in general, it would be true that given that we need heuristics, that all heuristics are good for the sake of heuristics. Don't think that that's the first one. I mean, a lot of people have bad heuristics in their practice, or start using, think, hey, I got to use a heuristic, and then blow up. That's the first one. The second one, the problem with regulation is, again, without skin in the game, you can always beat the system. Okay, and when I was a trader for 21 years, and I think that my career would have been only 10 years had it not been for regulators, because every time a market gets regulated, you hire a lawyer and try to find a way to try to make some money, because when it's regulated, it's an opportunity. Like you have regulation, you can't go short, on an uptake, on a downtick or something like that, and you create a structure that allows you to do that. So you start having arbitrages simply coming from regulators, and I thank the regulator for having financed half my career. Okay, so I tell you, this is, and you get shocked with telling me, yeah, you're giving money to people who know how to, maneuver systems. But all you need is a good lawyer. So regulators finance good lawyers, and finance traders who know. Japan is a market that was overregulated, and in Japan you can, with a good lawyer you can do anything.
I think our hosts get nervous.
Yeah, so they want us to leave now. But thank you very much for
Thank you, Nassim.
this thing, and thank you for listening to us.